Hello, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar series of the CMSA at Harvard University. And today we're delighted to have Yuanzhi Li from CMU, who's been doing a lot of exciting work on language models and both training small, powerful language models and understanding in more depth how they work. So as I always do, I'll offer to watch the chat. So if you have a question and you're not sure about whether it's appropriate, put it in the chat and we take a look and sometimes answer it. Questions are okay during the talk, and of course there'll be time for questions after the talk. So let's begin. Yuanzhi, please.
Can everyone okay. Can everyone hear me? Yeah, let me also turn on the thanks a lot for everyone to coming. It's my great pleasure to give a talk here. And today I'm going to talk about the physics of language models, in particular knowledge extraction and manipulation in language models. Okay, so as we know that this is a talk in the math department, which means I will not talk about anything mathematics because people are infinitely better at me than math. So I'm not going to embarrass myself. And but we will talk about potentially tons of interesting mathematical questions raised on the line of large language models and how we could think about it from a mathematical perspective. Okay. And the thing that I'm going to focus on for this talk is really knowledge, or the so-called factual knowledge. And the factual knowledge is the foundation of human intelligence. I mean, we have built so many different factual knowledge through our growth in the society from history. For example, from this Wikipedia article of Harvard University, I mean, there are a lot of factual knowledge here. For example, it's a Ivy League university. It's in Cambridge and is found in 1636. Okay. And of course, factual knowledge is one part of foundation of human intelligence. And if you want to build like an AGI system or artificial general intelligence, we need a model to memorize all those factual knowledge or most of those factual knowledges. So it can be used to answer questions that are reliable, okay, that are based on the factual knowledge. And in this talk, we focus on the ability or try to understand the ability of language models to memorize or to manipulate those factual knowledge. And also the talk will be pretty simple and you can stop me at any moment if you have questions. Okay, cool. So what are language models? Well, language models are just a model that takes in some input that are part of the sentence, and then you try to predict the next word in the sentence. Okay, for example, it's just you give an input of like Joe Biden is the American politician who is the 64th, and the model will predict the next word, which is the president, and you can keep applying this operation, and then it keeps generating the next word after the next word. So this is a language model. And regardless of the size, for example, GPT-4 has, rumor says is 1.6 trillion parameter. And then there's a ChatGPT and Llama and Mistral and Phi and tiny stories. Regardless of the size, they all have the same training objective, which is just completing the next word, okay, or predicting the next tokens. And for language models, what does it mean by memorizing some factual knowledge? Well, one way to think about it is like if a language model can keep reciting the next token with 100% accuracy, then it can recite the entire documents. Okay, so for example, I mean, for this particular sentence, if the model can generate the next token, which is that with 100% accuracy, and is with 100% accuracy, and hard to control with 100% accuracy, then it can, if it can keep doing that operation, with 100% accuracy, then it can recite the entire document. And going back to the Harvard example, if the model can predict the next token with 100% accuracy in the Harvard document, then it can kind of memorize the Wikipedia page of the Harvard University. Okay. And the point is, if a language model is trained on internet data, and believably internet data has the document of almost all knowledge of the human, right? For, I think, what is this? Okay. I think for, if the model is trained on Wikipedia data, then, or if the model is trained on internet data, then it contains almost all knowledge of a human. Then if a language model would be able to recite the next token of all those particular knowledge, would we call a language model actually master all the knowledge or understand all the knowledge of a human, okay, of human society, okay? In other words, for a language model, does it mean that minimizing the training loss or just being able to recite its training data is sufficient, or we consider that as a language model just memorizing all the factual knowledge of human, okay? So for example, this is a Wikipedia article of Harvard University. I mean, if a language model can complete, for example, when you give it private, it can complete Ivy League. And then when it goes to here, it can complete Cambridge, Massachusetts. And if you go to here, it can complete this word. I mean, if it's just training on internet data that are all those documents, and then it recites all the documents, would we consider this enough as a language model to memorize or master all the factual knowledge of a human or human society? Okay. So you may think that the answer is obvious, but for this talk, we are going to see that the answer is much more subtle compared to just memorizing those documents. Okay. So in particular for human, I mean, after memorizing the document, we are not only able to recite the document, we are also being able to kind of answer questions related to document, right? I mean, that we can answer simple questions like, when was Harvard founded? And in this document in particular says it's founded in this year. And if you actually recite the document with 100% accuracy, you should be able to answer those questions with 100% accuracy as well, right? And more importantly, you can also answer like those questions that you can infer from the document. For example, is Harvard older than Princeton? The previous document says Harvard is like the oldest university, right? And then you can infer from it, Harvard must be older than Princeton University, right? For human, we can actually extract the knowledge and we can manipulate the knowledge after we recite this paragraph.
Let me relay a question, which is for the word prediction. We know what we mean by 100% accuracy, but for answering a more general question, what do we mean by 100% accuracy?
We mean that we just answer, for example, when we ask when was Harvard founded, we can answer like the time that Harvard was founded with 100% accuracy.
So you would accept any form of answer?
Yeah, any form of answer that is
correct.
a
little bit subjective or a little bit. Okay. Anyways.
Yeah. Okay, cool. So we call this generalizable memorization, which means the model not only memorize the knowledge, but it actually generalize to kind of answer the questions based on the factual knowledge that it memorized. So it's kind of like it's kind of memorization, but memorization in a generalizable way, in the sense that it's not only completing the next tokens if I'm giving in the exact form of the document, but it also extract the factual knowledge and being able to answer questions based on that. So the main question we want to understand is, if the machine is trained to memorize the entire paragraph, which means it has 100% accuracy on completing the next tokens, does it automatically imply that the machines can generalize to answer those questions or to manipulate the question that it actually memorized? Okay. So basically, the question that we want to understand is if we train a language model that it recites this paragraph with perfect accuracy, which means it can actually complete the next token for this entire paragraph, then does it able to obviously answer, or does it able to answer the questions like when was Harvard founded, just by, just answer the question in the test time or up to some sufficient fine tuning to tell the model what's the meaning of when. Okay. And our work shows that the answer is much more complicated and it may actually surprise you. Okay. So in this work, we consider one piece of knowledge as really just one piece of name, attribute, and value tuple. For example, a piece of knowledge would be Harvard and found and this particular value, or Harvard and location and this particular value. Okay. And we consider knowledge extraction and manipulation tasks like, for example, given the name and attribute, extract the value. So this is like asking when was Harvard founded. Okay, so this is like given the name and attribute, you need to extract the value. And then there are also tasks like manipulation. We want to understand, for example, we want to ask, is Harvard founded before 1700? Okay, so this is like some simple manipulation of the knowledge. You have to extract the year that Harvard was founded and doing some basic comparison of the value. Okay, and we also consider knowledge search, which is super important, which is like you want to, after memorizing the topic of Harvard, you want to understand, you want to be able to answer the question like which university was founded in 1636. Okay, this is like given the attribute and the value, you want to extract the name. Okay, so these are three operations we want to understand. And we want to understand if the transformer is able to recite the paragraph of Harvard or recite all those paragraphs, then can it be able to do all those operations on the knowledge that it memorized? Okay, any questions? Okay, cool. So first of all, for GPT-4, it appears that the model can answer this question. You ask when was Harvard founded, it says it found correctly, says it's founded in this year and it's the oldest university. Okay, but here is like a tricky thing that we need to think about when we assess models like GPT-4 that are trained on internet data. So there are two possibilities that the GPT-4 uses to answer the question. The first possibility is GPT-4 just sees this answer in its training data. Then it just, complete the next token for this answer, right? For example, if the question, when was Harvard founded, was in its training data, and it also memorized this particular question or memorize its answer, then it's not really generalizable memorization. It's still just standard memorization to perform next token prediction. Okay, so what we want to what we care about is a second case where it doesn't see this question in its training data, but it only sees a Wikipedia article of Harvard, and then it try to infer the answer to this question just based on understanding when it's asking for time and where it's asking for place, right? And what is asking for, like, or whom is asking for a person, okay? So we want to know whether, we want to understand whether the model can do the second case. The first case is not interesting because it's just, still is just a standard memorization, just reciting the next words in its training data. So the second case, the model needs to do something non-trivial. But the main question is, for models like GPT-4, it trained on internet data and trained more than 1 trillion tokens. We never know whether the model is able to answer the question in the first case or second case, right? Maybe, think about, these are internet data, right? A question that you may ask is very likely to be already asked by someone else before. So if GPT-4 is trained on internet data, it may very likely be seeing all the possible questions already. And maybe it's not really generalizing from the Wikipedia article. It just sees the question and it memorizes the answer for those questions. Okay, so it's very hard to distinguish, to assess the actual kind of ability to generalize, to do generalizable memorization for models like GPT-4. Okay, because we cannot really assess its training data. I mean, even if we use like Llama on internet data, I mean, it's also very hard to assess its training data because maybe it's not the particular question like when was Harvard founded. Maybe it's like when was Harvard built, or when Harvard was founded. Okay, and those things are not exactly reciting the next token, but it's still just robustly reciting the next token. Yes.
Yeah, and you looked at like Gross's work on influence functions. Like I know they show some examples where it seems to be not exactly the same thing. For example, George Washington was the first president, but the sentences that seem to help predict that it's the first president are like similar to that, but not exactly the same.
Yeah, I think the point is if the model is trained on internet data, then even if like you like filter out all the exact questions from the internet data and retrain the model, there could be like very close questions that the model used. And the model just need to be a little bit more robust in terms of memorization, but still is not really like a knowledge extraction.
Thank you.
Okay, cool. So that's why in this work, we consider like a synthetic data where we can actually control what's exactly going to the training data of the transformer model. And we are going to train the model from scratch and just to understand the ability of the model to extract knowledge or manipulate knowledge. So the synthetic biography data look like this. So it's just a regular biography. It's like some person was born in certain places and whatever. So there are 6 attributes. There's birthday, birth city, university, field, and company city. So company and company city, they are actually related to each other. In particular, company city is a function of the company. Okay. And we generate a synthetic biography data for like 100K people. And the value of each attribute is like randomly assigned. So the values are kind of uniform. And each attribute has roughly 200 different values. Okay, and including the first and the middle and last name, each have like 1,000 different values. So we want to make the number of values to not be that large, just to have like a good sample complexity. Okay, so there are 2 versions of our data. There's one version where each sentence is kind of chosen from like 200 templates. Okay, the templates are generated by GPT 3.5. But for each sentence in the biography, we generate from like 200 prescribed templates and we randomly sample one. And another possibility is we just write the biography using Llama. Okay, and the experimental results are the same for both cases. So we are generally going to focus on the fully synthetic one for simplicity. Okay, so for this biography data, there's a very well-defined name, attribute, and value pair or tuple, which is a name, and then these are the attributes, and then there are the values. Okay. And then we train a randomly initialized GPT-2 model, which has 100 million parameters on the biography data set until the model has 100% training accuracy in terms of completing all the values. Notice that the model cannot have 100% training accuracy in terms of reciting the entire paragraph because the sentences have some diversity in it. So it doesn't know which sentence to use unless it sees certain amount of tokens in that sentence. But in terms of predicting the values, or in terms of completing the values, we train the model to have 100% accuracy. Okay. So for example, when it sees this biography, so here it's a faculty member at, and then in the biography it says Massachusetts Institute of Technology. So the completion of this particular token is 100% accurate, okay, in the training data set. So it means the model definitely memorized all biography of all 100K people, okay? So we train the model to memorize the biography of all 100K people. Okay. And then we take this pre-trained model, and then we ask a question, for example, what's the birthday of this guy? What's the birth city of this guy? Or where did this guy study? Okay, we ask 6 questions, each for one attribute. Yes?
Let me ask, I mean, do you give it any other language? I mean, how does it even know what the question "what is" means?
Yeah. That's what I'm
Okay,
going to talk about. Yeah, okay, cool. So can the pre-trained language model extract knowledge during inference time? And obviously no, because it doesn't understand the question at all, right? There is no question answering in the training data, so it doesn't understand like what or when is. So we need to fine-tune this language model, or we need to fine-tune the pre-trained language model so we understand the questions. So first of all, the pre-trained model memorize all the biography, and then we need to fine-tune the model to understand the questions so that it can answer the question. So what we do is we pre-train the language model so it completes the values with 100% accuracy. We pre-train it so it completes the value for all 100K people. And then we fine-tune the language model on the question answering pairs of the 50K people. And we can use LoRa or we don't use LoRa. Okay. I mean, it won't affect our result. But then we test the question answering of the remaining 50K. Okay. So we train on the 50K people, so we definitely understand when and what it means, right? Try to associate the when and what with the potentially with the biography. And then we ask a question answer with the remaining 50K. Okay, so this means that the model definitely understands the question. It sees like 50K of those questions, and it also sees a biography of all the people. And now the question is, if we train the model on the biography with 100% accuracy, and then we fine-tune the model of 50K people to answer the question with 100% accuracy, does it mean that the model answers the questions for the remaining 50K with 100% accuracy or with good accuracy? Okay. Any questions? Yes. Yeah, just knowledge extraction at this point, but we will talk about inference of knowledge later. So the result is kind of surprising. So the model is almost like random guessing in the remaining 50K. Okay, so here, this one is like in the bracket is the training accuracy, and the bold form is a test accuracy, which means in the remaining 50K. So you can see no matter how you adjust the LoRa rank, if your LoRa rank is very high, then the training accuracy is almost 100%. But the test accuracy is just like random guessing. Okay. And then you can reduce the LoRa rank, so you kind of force a model to modify the pre-trained model less. And you can see the training accuracy decreases, but the test accuracy stays the same, which is like random guessing. Okay. So you can see even if you change the model size, so this is like the GPT-2, and this is like larger version of GPT-2, and a larger and larger. Even if you make the size larger, even if you make the model size larger, it doesn't really change the effect. Okay, so this means even if the model memorizes knowledge 100%, so it memorizes a biography with 100% accuracy, and it's fine-tuned with like enough question answering pairs to understand the question and answers, it just doesn't really generalize to answer questions for the remaining 50K. Well, it can still recite the paragraph, but it just cannot answer the questions.
Excuse me. Can I ask what are the numbers in the parentheses? Like, what's the difference between?
So this means for language models, reciting the paragraph definitely doesn't mean that it kind of being able to use the knowledge or being able to extract the knowledge. And this is kind of super important because people always believe if I train the model on internet data and I memorize everything, then it's fine. I just need some fine tuning to understand instructions, then the model are good. But this one says no. Okay, it memorizes everything and it's fine-tuned with instructions to understand it, but then it still cannot extract the knowledge for the instructions for the kind of question answer that it hasn't seen. Okay, so there's something fundamental for transformer models. You cannot say I train on internet data and I memorize it, that's all.
Excuse me?
Okay.
Can you
So
hear me?
why can't a pre-trained language model extract knowledge? Well, we try to understand this phenomena by understand where did the knowledge store in a pre-trained language model. Okay, so where does the knowledge stored in a pre-trained language model? So what we do is we take the input sentences and we go through the transformer model. And then for each token, it's going to be mapped to like a token vector, token embedding vector. Okay, so in the last layer of the transformer, it maps the token to a token embedding vector. And we want to understand whether the knowledge are linearly stored in the token embedding vector or not. And we show that whether the knowledge is linearly stored in the token embedding vector actually implies or has a super high correlation with whether the transformer model can extract the knowledge or not after fine-tuning. Okay, so if it's stored, so ideally we want the knowledge to be, we want the kind of the knowledge of Alice to be stored on this particular token embedding. Right, we want it to be stored in here. But think about the next word prediction objective. Right, it doesn't really need to store the knowledge of Alice here because it doesn't need to predict, for example, the birthday of Alice until it sees this in. So in particular, it could store the knowledge of Alice in this particular token, right? Or in the token embedding of this particular token. And it could study, it could even worse, it could store the knowledge of Alice, like start in this, or store the field of Alice in this particular token, in this study token. Okay. Okay, cool. So basically it just means, I mean, if the model recites a biography, it doesn't mean that it stores the knowledge of Alice inside Alice. Okay, it may be able to store the knowledge of Alice in this in or store it in the studied. Okay. And notice, yes?
We fine-tune it on the remaining 50K token, then it should learn to associate Ben and Alice to birthday. Like then there should be a connection which should be stored between these ones when we fine-tune.
Yeah, so the main point is when you fine-tune, it doesn't really associate them. Because if it associate them, then it should be able to answer the question on the remaining 50K. But it seems when you fine-tune on the 50K questions, it fails to associate this, for example, studied with like where. So it just kind of memorized the 50K examples that you fine-tune, but it didn't really associate with the studied at the biography.
Yeah, I mean, it could store the knowledge with the embedding of a given token, but I don't see why that's required at all. Again, it seems equally valid to store the knowledge in many ways in the words.
Yeah, so that's what we want to show. If the model stores the knowledge in this computer, in this studied, then it's not going to be able to fine-tune to answer questions. But if it stores the knowledge in like Alice or more closer to Alice, then it's able to be fine-tuned to kind of doing question answering. So it's kind of like where the knowledge is stored after it recites a biography, decides like whether the model can be fine-tuned to answer questions or not. Yeah, so basically what we take is we take those blue things and then we use linear functions on top of them to predict the right one or those values. So the blue things are just the tokens before the values. So in particular, if you see this ad, because it can recite the entire paragraph, so after seeing the ad, a linear function should be able to predict Massachusetts Institute of Technology with 100% accuracy because it is reciting, it's able to recite the paragraph. But what about seeing this in or more importantly, after this particular token, would a linear function be enough to predict this thing? I mean, a nonlinear function would definitely be enough because the knowledge is there. But we want to understand whether a linear function is enough or not, which means whether how easily decodable the knowledge is. Okay. So basically what our key observation is, if you train on the biography data, the language model actually doesn't really store according to the name, attribute, and value tuple that we wanted it to be. So it doesn't store it like Alice study MIT, but it's more or less like storing the knowledge as like Anya, and then his birthday, and then Princeton, and then MIT. Okay, so it's kind of stored in a weird tuple instead of the correct name, attribute, and value tuple that we want it to be. So that's why it's so hard to fine-tune the language model to answer questions, because there's no study in kind of this storage. So it's very hard to associate like where to this particular value or particular attribute. Okay. So in particular, we can see, so we want to use those tokens to predict the kind of, we want to use a token linear function over those token embeddings to predict the attributes in the biography. Okay. And when you see this token, of course, the next token, which the next value, you will predict with 100% accuracy. Okay. But the token after the next token, you can see it's almost like random guessing. Okay. So how do you rate this paragraph? This is basically the first token, which is this guy. And of course, this guy, before this value, there's only one token. And this token will predict this value with 100% accuracy, which is here. And then this is like the second value, which is this MIT. And before that, there are from and at. You can see from at, a linear function would predict this MIT with random guessing accuracy. But at a from, it will predict MIT with 100% accuracy. And then there's communication, there's in, from, and at. You can see they are all the from and at are all random guessing. And the model only has a degree in communication after this in. Okay. Even if it sees like from, even if it reads a paragraph until here, it has no idea, or at least a linear function has no idea what's the kind of field that or this person studied. Okay, so it's kind of stored, it kind of only decode the knowledge to be linearly extractable until the very end. Okay. Yes.
This is an issue for the pre-training, not the
yeah, this is an issue for pre-training. So in the pre-training, it's not really storing the knowledge of this person in a very decodable way close to his name, but it's actually store the knowledge like after you read the entire paragraph. Okay. So how do we mitigate this problem? How do we actually make the pre-training to force the model to store the knowledge in the correct position? So we show that data augmentation can mitigate this issue. So we consider 3 types of data augmentation. There's a full name data augmentation, which is you just replace all this she by full name, by the person's name. And then there's a permutation, which means you just permute the sentences, and you always keep the full name to appear at the beginning. So for example, you can permute the sentence, this sentence, let's say, so this sentence, I mean, the Princeton was here, you cannot permute it to make it at the beginning. Okay, and you didn't really change the sentence, just do some permutation. Sorry, this example is a little bit bad, it changed the sentence, but permutation just means it doesn't change the sentence, it just permute the order of the sentence. And then there's a diversity rewrite, which you change a sentence, but you don't really permute. Okay, so you just rewrite each sentence using different wording, and you don't permute. And we see that all of them are going to improve the question answering abilities of the model by a significant amount. And also it forces the model to store the knowledge in the particular in the token embedding of that particular person's name. Okay, so they are kind of highly correlated. So here is the result. Okay, so I mean there are different ways. So here is basically the augmentation you use. For example, full name or permutation, and the number means you do how many times you do it. For example, you permute 1 time per person, or 2 times per person, 5 times per person. So this permute 1 is particularly interesting. It means that for each individual person, the sentence ordering are different. Okay, so for each individual person, the sentence ordering are different. They are randomly permuted, but you only see like 1 permutation per person. And you can see it doesn't help at all. Okay, it's just still stay at random guessing accuracy. Okay, and but if you permute like 5 times per person, you can see the accuracy grow higher. Okay, grow much higher. And the best one is you use permutation and you also use full name. Okay. And the most interesting observation is you can see that it has like almost 100% correlation of this question answering accuracy with how the knowledge is stored in the pre-training. Okay, you can see the best ones are, so the best ones are these two, the permutation and the full name. Okay, so these two, you can see for these two, it actually knows, or a linear function can decode the knowledge immediately after the person's name. So if you use like permutation plus full name, okay, or you use like, oh, this is multi 5, which means you use diversity 5 plus permutation plus full name. So in this setting, it actually stores the information of a person just immediately at its name. Okay, linearly decodable at its name. Okay.
And you've matched the number of epochs, right? Like this the smaller data set you repeat to get the same.
We all train for a very long time, so the training accuracy is 100%. So it's already kind of memorizing the training data.
So you say at that point it's the end anyway. So it doesn't
it's the end anyway.
Right,
the accuracy cannot improve any further on training data. Yes.
You have to take the she and he and so on, so that not everything is at the right place.
I mean, full name is good, but without full name, you can see it also works.
Okay.
Yeah, full name is like a good augmentation, but you don't really need that.
Okay.
Yeah. But the point, I think just from this paragraph, you can see diversity is the most critical thing. Yeah, diversity gives you the best accuracy, while permutation is a bit better than full name. So diversity is better than permutation.
So does it mean that actually the model is actually focusing on the syntax instead of learning the factual knowledge? Since we're writing down, so is it the case? So I don't know.
I mean, not really, because the rewriting means we just sample 5 different sentences from the 200 one. Yeah, so it's still from the syntax are still pretty easy, but it's just one person has like sample 5 sentences from the 201 instead of 1 sentence from the 201.
But you would say the data is consistent with all of these data augmentations working by putting the knowledge into the embedding as opposed to other mechanisms. And it's just how well they're doing that.
Yeah, you can see, for example, here, the multi plus full name is very bad at this city field. And for this city field, you can see it's not really putting the value in the embedding. It's only at the very end. So only for this city field, for all the others is almost perfect. And for all the others, it's really putting it in the person's name. So it's, yes?
You show the improvement and I think add more data augmentation types, but don't seem to show the improvement that you get when you do not have diversity, but only the permutation of all these. Because you are showing that diversity is really important, but I wonder whether you would see the full name is really important if you only did that.
Here, this one is only full name. So the plus means the number of the augmentation we use. So single means there is no diversity. And then we add full name. You can see full name is helpful. And then when you have permutation, it's also helpful. These ones are only permutation. And then these ones are diversity plus permutation plus full name.
Did you try taking half the names and doing the data augmentation and then?
Yeah, I will talk about it.
Good.
Yeah. Okay, cool. So also, I mean, the most critical observation is basically this correlation, right? The accuracy is kind of almost perfectly correlate with whether it stores a kind of value linearly in a person's name or it stores it very later in the biography. Okay. Yeah. And then, I mean, we also consider the kind of only doing augmentation on a subset of people. So we call this subset of celebrity, which I mean, in practice, it's like you have celebrities whose data are rewritten for multiple times, but then you have some particular person, such as me. I mean, my biography is probably just only on my internet, website page. It's not rewritten anytime. Okay. So the question is, if you only rewrite the data for like 50K of the people, and you only have like QA fine-tuning or question answer fine-tuning on this 50K, would it help, would it transfer for the remaining 50K where the data has no diversity and has no question answer? And the answer is yes, actually. The answer, the remaining 50K without any augmentation and without any question answering, the accuracy is still growing very significantly. Although it's not as good as if you do the full augmentation, but still grow very non-trivially. Okay, you can see here, this is a celebrity, and then this is single plus permute one. And as we recall, single plus permute one, this was the original accuracy if you have no augmentation at all for any people. But if you have augmentation on the 50K people, or the strongest augmentation on the 50K people, then you can see the accuracy of the remaining 50K now is very, very high. Okay. So it's kind of, if you have the 50K people, then it kind of forces a model to store the knowledge in its name. And then it also transfers this storage mechanism to the remaining 50K. Okay, which is kind of surprising. Yes?
You try to do like a chain of thought kind of setup here where you ask the question like when was this person born, but you give it also like you can take as you don't need to give a single word answer, but you can like to me it seems like this is like because it has never associated this name directly with a location or where this was born. It needs some time. It needs some amount of tokens to like get that knowledge.
Yeah. Actually, for our data, I mean, I showed it badly, but for our data, we do the answer does come with the person's name and then plus was born, and then plus the actual answer. So even in that case, it doesn't really help. Yeah. And we also try to even train those like thinking tokens. Yeah, it also doesn't help. We have all the experiment in the paper. Okay. Yeah, I think this is a really interesting observation, and it will be cool to understand the mathematics behind like how does a model store knowledge. In particular, why would the augmentation on the 50K transfer to the remaining 50K? Like it's transferring the way to store knowledge, which is kind of a very non-trivial operation. Yeah, so this is about knowledge extraction. And next I want to talk about knowledge manipulation, which is whether the model can actually answer questions that are functions of the value, but not the value itself. For example, we want to answer a question like, is Alice's birthday even? Or is Alice's university rank higher than Bob? Okay, this requires the model to extract the knowledge first, and then apply some very simple function of it. Okay. And first of all, can language model actually manipulate knowledge? Well, surprisingly, the model, even for GPT-4, its ability to manipulate knowledge is really, really bad. I mean, for example, if you ask, was Donald Trump born in an even day? And GPT-4 is actually going to get it wrong. Okay. And then you ask it, but it actually knows what's the birthday of Trump. And then you can ask it again, what does it mean by even? It definitely knows it's even, what even means. But it seems that the model cannot extract the knowledge and then doing one step of manipulation. Okay. And there's some statistic here, for example, for celebrity, okay, for Wikipedia celebrity. So if you ask about the birthday or birth year, then it's 99% accurate, okay? So GPT-4 definitely memorized all the Wikipedia articles and it's able to extract knowledge for the celebrities, probably because the training data is already diversified for the celebrities. But now if you ask it for this particular celebrity, and we also add occupation, city, and year to disambiguous, and you ask it what's the birth, whether it's born in an even month or not. The GPT-4 accuracy is actually random guessing. Okay, just 50%. It's exactly random guessing. Okay, so even if it knows the birthday, it cannot really manipulate this knowledge at all. It cannot even do like an even or odd. Okay. And if you do like ranking, it's almost random guessing for like older people. For like more recently born individuals, it's actually better than random guessing. But potentially this is because the older and the younger question is actually asked by many people, right, on the internet, maybe just reciting those data.
But then if you do a chain of thought and you ask it to first say the birthday and then, and then to answer the question.
Yeah, then it will be 100% accurate because it can answer the question correctly. And then of course it knows what even and odd means. But this particular question, for human, we don't need a chain of thought. We don't need to write it down. I mean, we can do it in our brain, but GPT-4 cannot do it in its brain, which is kind of a pretty significant limitation.
Well, there might be, maybe people are using chain of thought. There are psychological differences between different.
They are using chain of thought, but it's in its brain.
Yeah.
We don't write it. But for GPT-4, it just cannot do chain of thought in its brain. It has to write it down, which is pretty limited because then the answer of GPT-4 has to be super long, while human can do many steps in its brain. So even GPT-4 surprisingly cannot answer super simple function of the knowledge. And why is that? Is this like an even or odd birthday just too out of distribution? GPT-4 didn't see any question at all, or there's like fundamental difficulty. Okay. So we still use our synthetic data to kind of try to understand this question. Okay, so we take the pre-trained language model on the biography data with the strongest possible augmentation, which is this diversity plus permutation plus full name. So if we have this augmentation, we know that if we fine-tune on like just answer the questions, it has 100% accuracy or almost 100% accuracy. Okay, so knowledge extraction is fun. And we want to understand, can the model be further fine-tuned to just answer this even or odd question? Okay. So if we further fine-tune the model on the knowledge manipulation task, can it actually answer the question directly without chain of thought? Because with chain of thought, it's easy. It's just like you do an extraction and then you kind of just understand that the answer is then you do a manipulation of the extracted answer. So that is definitely doable. But what about without chain of thought? Can the model do the thinking in its brain? I mean, it's not hard thinking. It's actually very easy thinking. It's just more tool. Okay, can the model do more thinking in its brain without writing it down? And what we show is actually no, okay, or mostly no, okay. So for example, for this mode 2 question, I mean, first of all, this is the number of training data you have, okay. So you can see even if you train on like 5K or 10K people, okay, which is, I mean, more than enough for the model to understand what mode 2 means, because mode 2 only has like 10, only has like I mean, the birth months only have 12 different values. And to understand mode 2, you just need like 100 training data. But even if you have 10K training data, you can see the mode 2, the model still performs pretty badly. Okay. And this, and the part we will focus is like, we should focus on, I mean, we should focus on this particular entry. Okay, so this is the particular entry. So this train with hint means we train with both chain of thought data and without chain of thought data. So chain of thought data kind of teaches the model this birth month is associated with this answer. Okay, so we train with both chain of thought data and without chain of thought data. And we only test on the data that are without chain of thought. Okay, so chain of thought data should be able to teach a model that this like 1 is associated with 5 more 2. But then if you test it without chain of thought, you can see that the accuracy is not really kind of very good. Okay, so it just lacks the ability to think in its brain unless it see enough data and then it just performs some kind of memorization. Okay, it just lacks of this generalizable thinking ability to think, especially for ranking and subtraction. Okay, for ranking and subtraction, even if you have 50K data, it's still random guessing. Okay, it's like ranking, which means whether the person's field is like ranked higher than the other person's field, or like what's the gap between one person's field and the other person's field. Okay, so for those, even if you have 50K data, it's still random guessing. In particular, with chain of thought, the model should be able to learn the ranking operation with only like 1,000 examples, because I mean, it's a pretty simple function. And we have the chain of thought. We taught the model how to think, right? The chain of thought means this people's university is here and this people's university is this guy, and this people's university rank this one, and the other people's university rank in that one. So the person's university is ranked higher than the other. So we teach the model how to think, but we just ask the model to, in the test time, to give the answer directly while thinking in its brain. But the model just cannot do it. Okay. So the model just cannot really think in its brain. So its ability to manipulate the knowledge is quite limited. Okay. And the training on chain of thought, which means you train to teach a model how to think, it doesn't help the model to generate the answer correctly. Okay, which means, this means like, for example, for many knowledge language model benchmarks like MMLU or those benchmarks that ask the model to predict the answer directly, it's kind of skeptical that the evaluation result is actually valid, because even or all, they cannot extract the knowledge and do a single operation on it. Not to mention like MMLU, where you ask a pretty complicated question and you ask the model to generate the answer directly. I mean, it's very skeptical whether the measurement is accurate or not. Maybe the model actually just sees the answer in its training data. Okay, I mean, we give evidence that like all the type of assessment of language model without writing the intermediate steps is kind of, the result is kind of very skeptical. Okay, so large language models don't really have thinking ability in their brain. Like even GPT-4 cannot think about even or odd in its brain, okay, which is pretty bad. Okay, so this is one fundamental limitation. And the other fundamental limitation I want to ask is this inverse knowledge search, which means I want to give I just give the attributes and the values, and I want the model to search what is the name of the person. Okay, so who was born in this one and studied at this one, and whatever. Okay, so this is critical for intelligence because, for example, if you want to answer the, if you want to write an essay, we need to search from the data that are stored in our brain and then try to match a given property, right? We want to find evidence where a person is like working very hard and then is success, right? This is like an attribute, and we want to search for the correct name of that person. This is the root of intelligence. And can like language model perform this operation or not? For example, when it reads this Wikipedia article that talks about a famous mathematician at Harvard that studied number theory, can it actually answer the question like name a mathematician at Harvard who works in number theory just by recalling this article and extracting the name? So can the language models act as a database or not? And from the synthetic data, we see that the accuracy is basically like random guessing, unless you do some crazy data augmentation. Okay, you can ignore all the things with reverse. Those are the belows are just like the regular training. You can see even if you fine tune on the question answer to search for the names, on the remaining people that are not really like questions are not really in the training data, then it's just going to be like random guessing accuracy. Okay, it's not even better than random guessing, it's just exactly random guessing. Okay, so it just means the language model cannot be used as a database. So it stores the person's name with its attribute correctly, but then if you ask the attribute, you want to know the person's name, there's a one-to-one correspondence, but the model cannot reverse this operation. Okay, it's just like a one-way function. So it maps the person's name to its attribute, but then it cannot be mapped back, or it cannot be decodable. It's not, there's like a one-to-one mapping, but it's not really decodable. So it stores it in a like very non-decodable way. So it means the language model probably cannot be used as a knowledge base. And this also limits the potential application of language model. And it's also an interesting mathematical question, like how does the knowledge start? Why is it just so hard to inverse it? Or is there a way to help the model to perform this search? Okay, because without the search, it's kind of almost saying that the model has no intelligence or no creativity, right? The only thing that it can answer correctly is basically the one that it already knows or already reads in its training data. And if you ask it to find something in its training data, or to like, for example, identify the correct mathematical theorem to be used for this particular, to be used to prove this particular thing, the model just cannot do it. Unless it sees like a training data that applies this mathematical theorem on this particular thing or very similar thing, they just perform like a forward pattern matching. But it cannot really search through the theorems that is stored in its brain and then extract the correct one. Okay. Yes.
I have a question. Like, do you think, I don't know how what it is, but do you think you can guide the models like do like the database flow, like software? I don't know whether it's possible.
But you have to write down all the knowledge of the model that's stored.
Exactly,
yeah, it's pretty hard to do so. Yeah, it's just like you need the model to write down all number theory theorems and then select the correct one. That's very hard. Yeah, so that's basically the end of my talk. And for future directions, we are working on the scaling laws, which try to understand how many pieces of knowledge can be stored in a language model of size M. And we can see that it's actually a very linear line. Okay, it's just a linear line, and the slope is like 20. So which means that for a language model of size M, it can store like M over 20 pieces of knowledge. So that means for like a 1 billion parameter model, it can store 1 billion divided by 20, which is 50 million piece of knowledge. And is 50 million piece of knowledge enough for elementary school student? I think that's enough. I mean, we need to build some mathematical model to estimate that. But with this scaling law, we can kind of actually understand what's the model size enough to simulate like an elementary school student. Okay, and also we want to augment the model with a database because it just cannot really extract the correct theorem. I mean, that's why I think the models are not really clever in math because it really just cannot extract the theorem. So we need to give the model some database to help the model extract the correct theorem or correct like tools to be used or correct names or correct evidence. Okay, so those are the interesting future directions. Yeah, that's the end of my talk. And thank you everyone for coming.
Thank you. Very interesting. Questions? There's a question in the chat from Mohammed Khalifa. Would you like to ask it?
Yeah, sure, I can ask. So I have a question that I've been thinking about since the beginning of the talk. And it's basically, why should we expect a model trained to predict next word to be able to internalize the knowledge it sees? I mean, even for us humans, if we, for example, memorize a poem or, or something like that, and then someone asks us, like, what does the fifth verse talk about? It's going to take us a while to cite the poem from the beginning and then arrive at the fifth verse and then know what's talking about. So I feel we're asking too much from the language model by just training out to predict the next word and then finding out that it's not really good at doing this knowledge manipulation task. Isn't that kind of expected?
At least when we do the augmentation, the model can do those tasks. So this means like we have to rely on a certain way of training the language model. So we don't need to change the objective, but we definitely need to find the correct data distribution or correct data to train the language model so it stores the knowledge in the correct form. Or we can use different ways of different training data to kind of teach the language model what does it mean by a particular attribute and value. So if the model understands the attribute and value, then it could store it in like the correct form. So it's like when you read a biography, you kind of know like the birthday and then the actual value is kind of the correct attribute and value. But then maybe there's some word which are just like random words. They are not associated with the attribute and value. So we have to teach the model to understand them so the model can store the knowledge correctly.
So you agree it's not going to be possible?
Everything are like values. So there's no real, there's no like each word corresponding to a particular attribute. So there, the model can only recite the entire poem. But for something like a chemistry, for example, chemistry article, there are a lot of attributes. For example, the color of the matter, like the make of the matter, the smell of the matter. And we have to teach a model, those are the actual attributes. So, I mean, what our work is just to say like data augmentation, which means you rewrite and you kind of keep the irrelevant word diverse, while keep the relevant word stay the same. It's a way to teach a model to kind of understand the correct attribute and values and do the embedding correctly or do the encoding correctly.
I see. Thank you.
More questions?
Yes.
Is it possible like instead of separating the fine-tuning to the pretraining phase, if it is done simultaneously when the network can associate like the terms like a particular birth date with a particular birth. Like once you have pre-trained and you are fine-tuning on top, it's like it has a separate database of pre-training which it might not use for fine-tuning at all.
Yeah, so that's a good question. So for this manipulation task, we have the pre-training. So we actually insert those data into the pre-training and it doesn't help at all. So for manipulation, we insert it into the pre-training and it just doesn't really associate. But for the knowledge extraction, if you insert into pre-training, it definitely helps. But it's helping in a very weird way, which means the kind of question answering accuracy is going to 100% the first, and then the biography accuracy start to increase. So it's kind of the model first memorize the question and answers and then associate the question with the biography instead of doing the other way around. So it's kind of having like the wrong way of learning. So that's why we kind of doing the pre-training first and then fine-tune it. Yeah, because that's how people do, like they train a language model on internet data. And then if you play with the, for example, llama base, it's actually a really terrible model. But if you fine-tune it, start to do something really good. Yeah, so that's what people believe. As long as I pre-train, I just store everything in my language model, and the fine-tuning could be able to extract the knowledge. And what we show is that's not the case. Yes. Yeah.
So before the augmentation, after the augmentation, presumably the model achieves like similar, like very high 100% accuracy on the biography, right?
Yeah.
So why does the transformer converge to like the less good representation without the augmented data?
Yeah, that's a very good question. I mean, that's the question we want to understand, but we don't understand. At least we observe that with augmentation, the kind of representation of the data are different, although the accuracy are the same. So then the next step is try to understand like what's kind of the mathematical principle behind it, and that we haven't really understand yet.
Jesse, would you like to ask your questions?
Sure. So for the data augmentation and the biography experiments, I noticed that you kept the names towards the beginning of the sequence, but frequently in practice, the entities that you want to recall the information for can occur in other locations. So have you like tried the data augmentation experiment where you like say move parts of the question before the name and see if that still results in good representation learning for that name?
Yeah, that's a good question. So I think the answer is, for example, if a person's birthday appears before the person's name, then the model just cannot really answer questions for this person's birthday, because that's exactly equivalent to like inverse knowledge search, right? It's just saying, I associate the name of the person with the birthday, and now I want to answer what's the name of what's the kind of birthday of the person. So I can answer what's the name.
Oh yeah, you definitely want the information.
That's my next word prediction objective. But then now I need to answer what's the birthday of the person given the name, which is an inverse knowledge. And that's actually not doable by this experiment. So if we don't put the full name of the person at the beginning, then whatever is before the full name of the person, those knowledge the model just cannot extract, because that's like an inverse.
Yeah, you definitely want. So you definitely want the things you want to recall to appear to the right, because then your learned representations of the person's name are going to receive gradients. But the question I was asking is like, did you see if some kind of data augmentation where you sort of like had more natural looking sentences that perhaps had the person's name appear not in the first token of the sentence, but maybe like 5 tokens later or 10 tokens later, with all the salient information still appearing to the right of that person's name? Perhaps that would have helped the model learn more robust representations of that person's name, and therefore make it more useful for the inverse knowledge experiment.
Yeah, that's a very good question. So we do have for this inverse knowledge experiment, we do have like a llama rewrite data. So for llama data, the person's name, there are some chance that it doesn't appear at the first token. And the language are pretty diverse. And sometimes the person's name even appear in the middle, or at least after 10 or 20 tokens. And that doesn't really help. I mean, the observation of the observations are still the same, unless the person's name appear after certain attributes. Then it definitely helps inverse knowledge search, because then it's not an inverse knowledge search. It's a forward knowledge search. So if it doesn't appear after certain attribute, but it just appear like there's like 10 random words at the beginning of the sentence, it won't really help the model.
Oh, that's interesting. And for the negative result for the inverse knowledge search, did you guys do any normalization for the attributes and values? Because so for example, Princeton might appear in like, say, different forms for like 2 different entities, but you want the model to perhaps learn like a single good unified representation of Princeton to which it associates both of those entities.
Right now, when we ask the attributes, we ask a sequence of attributes and we make sure the name of the sequence is kind of unique. So if there are like ambiguity, then that's a different question.
Mm-hmm.
Yeah, but now we didn't consider ambiguity for our question.
Yeah, I just mean like thinking of like the knowledge that you're representing as sort of like a knowledge graph, right? Like you kind of want there to be a single node for an attribute like Princeton that is simultaneously linked to like 2 entities like Mary and Bob. And so I was just wondering if like for this inverse knowledge search experiment, you normalize those attributes in any way. Because otherwise the task falls
right now
to
we
the model
didn't
to
do it.
like
We just
compute that
use
implicit
the
equality.
standard like next word prediction objective. But I think normalization would be an interesting solution to see if it can fix the inverse knowledge search. But my conjecture is no, because I think it's just because the model store the knowledge in like a one-way function. So you can, from the name and attribute, you can extract the value, but not really the backwardly. So I think even after normalization, it probably still store the knowledge as a one-way function.
That's helpful. Personally, I'm a bit more optimistic, but those are all my questions. I think this is awesome work.
Yeah, thanks. Yeah, that's a really good suggestion. I mean, we are happy to try it.
I have a question. So with your model synthetic data, it's consistent with attributes which it's good at answering questions about or embedded or carried with the embedding of the token that has the attribute. And that's very limiting. I mean, that means that most of the model parameters don't even enter into that. It's just the parameters of the embeddings.
Yeah.
And do you believe that that's also the case for a large language model like GPT? And is there evidence for or against that?
Oh, it's not the parameter of the embedding, it's the output of it's the token embedding of the transformer.
So it's the output, it's not the input embedding, it's the output.
Yeah, it's I mean, so transformer has a particular output, which is like number of tokens. And then you kind of do like a softmax on it and then predict the next token. But before that, there's like an embedding layer of the token. So it maps each token to a vector. And that is like called the token embedding. And we are actually looking at a linear function over that token embedding.
Well, there's an input embedding, which is just, again, learned to associate each token, then it runs through the transformer, and then you can call that the output contextualized.
Yeah,
embedding.
the output
and what you're saying is the contextualized embedding has to contain.
Yeah.
So it can see the other parameters, but it's still quite limiting. I mean, it means that the dimension of the embedding has a lot to do with the maximum the maximum number of attributes would depend in principle on both the model size, but on also the dimension of the embedding. And that last number, the dimension of the embedding, would be very crucial according to this.
Yeah, I think just according to our experiment with the augmentation, the key thing is we show this one-to-one correspondence of whether it stores linearly in the token embedding or not, versus whether it can be fine-tuned to extract the knowledge. So that's basically the key. If we consider more complicated functions, of course, we can extract more knowledge, but then it may not be associated with whether it's extracting the knowledge.
But you could test the same hypothesis not for GPT unless you work at OpenAI, but you could test it for Llama or some other open model that attributes which it's good at answering your questions are there in the contextualized embedding and can be seen by a linear probe, right? You could test that.
Yeah, I think the GPT model is trained by us. So the Llama and as I say, the Llama and whatever Mitra or whatever UFI language models, they all have the same training objective and almost the
Yeah.
same architecture.
Right.
So I don't think, I mean, changing to Llama probably won't change anything because it's a
Oh, yeah,
same.
no, that wasn't, I was just saying that you need to be able to get at the embeddings and, you know, to test this hypothesis. I mean, are you testing it or do you believe it?
I think it's the same conclusion hold because we do try GPT with different sizes.
Okay.
Yeah, for Llama, the difference between Llama and GPT
Yeah.
are essentially nothing. They are just
Yeah,
the same model.
I agree. Okay, so then what's the embedding dimension of well, I mean, for GPT 3.5, it's like 10,000 or something, right?
For the model we test, the embedding dimension is like 1,000 to
Yeah,
like
your
2,000.
simple model, and now I'm
Yeah.
asking for a large language model like GPT 3.5 or GPT 4.
That is like too large for us to train, but for Llama it's like 4K. For Llama 7B, the embedding dimension is 4K,
Right,
which is not significantly bigger than our model.
right. So then it should not be able to remember that many attributes.
Right.
Or else it should not be able to answer questions, as you say, knowledge manipulation based on that very many attributes. So that
Yeah.
would seem like the limiting factor. That would seem like a much bigger limit than the number.
Well, also we are reporting the test accuracy, so the actual dimension doesn't really matter that much because if the dimension is very large, you can minimize training accuracy for this.
No, but according to your hypothesis, if it's required to realize all the attributes in the contextualized embedding, then the dimension matters a lot because that limits how many attributes you can realize.
Yeah, I see. Yeah, I think, but the total number of like attributes are like, or attributes and values for each attribute, there's only 200 values.
Yeah.
So in principle, if you have like 200 times 6, which is 1020 dimension, is
Oh, yeah,
enough.
you can do it with 6 attributes, but there must be, you know, hundreds of attributes. If you look at like knowledge graphs, there are many tens of
Yeah.
common relations.
Yeah, but for our setting, it's only 6.
No, but now we're asking about the real thing, right?
Yeah.
About the real GPT or the real, you know, Llama with answering real, you know, a large selection of real world questions. How many attributes can it answer questions about?
Yeah, that's a good question. I mean, I don't really know the answer.
Yeah, okay. More questions? If not, let's thank Yuanzhi for a really very stimulating and interesting talk.
Okay, thanks.
Thanks. So next week we'll have Sean Butt, who will talk about Lemma, which is a Llama fine-tuned on mathematics. So I hope to see you all there. Bye.